So welcome to this session 3 of the tutorial on symmetric nets and symmetric nets with bags. In this afternoon, we will present symmetries in symmetric nets. So we'll show you why we use symmetries. We'll define symbolic markings and symbolic firings, and we'll show how to build the symbolic reachability graph. Then afterwards we'll present symmetric nets with bags that are an extension of symmetric nets, and we'll show the syntactic extensions as well as the firing rule and also the unfolding that can be achieved to obtain a symmetric net when this is finite. And finally we'll conclude the tutorial. Okay, so let's have a look at symmetries in symmetric nets. Up to now, you know about symmetric nets and their syntax and semantics. You know how to build a reachability graph. A reachability graph can be used for analysis, and you have experimented with the Cosivere platform to practice these concepts and formalisms. So now we'll see how to use the symmetries and give the feeling for symmetries in order to reduce the size of the constructed structures. So let's take again the introductory example of processes that want to access a critical section. We've seen this morning in this example that from the initial marking here, you can have several similar firings. So T1 is enabled with any of the process's colors, C1, C2 and C3. And these three firings are very similar. So here only two of them are represented. The one where we fire T1 with C1 here, that gives this marking M1, and the one where we fire T1 with C3 that gives this second marking M2. Okay, they are very similar in the sense that initially we have in idle place the three processes, and we have the resource. And in markings M1 and M2, we only have two processes remaining in idle. The one we have chosen to fire the transition is now in waiting, and we have the resources as well. So they have a very similar structure. Two tokens in idle, one in waiting, and one token in resource. Therefore, we can think that we want to represent them the same way, and we could say that if we take color C1, so here, it's similar to color C3 here. It plays the same role, right? And in fact, we can move from T1 C1 to T1 C3 just by replacing C1 by C3. And similarly, from marking M1, we can get marking M2 by doing the same operation, so replacing C1 by C3 and replacing C3 by C1 and leaving C2 as C2. So if you do that element by element, you see that idle contained here C2 and C3. You apply this transformation in the middle, and idle contains now C1 and C2 as it's here. The same applies to waiting. So waiting here contains C1, and we apply the transformation, it should contain C3, and that is the case here. And res is unchanged. Okay. So we applied permutation to the transition color, and the markings that are obtained are the same up to this permutation. So we can represent the set of firings by using variables instead of the actual values of the colors, and the initial marking could be represented by three variables, x, y, z, sitting in idle. So we don't say x equals C1 or x equals C2 or whatever. There are just three of them that are in idle, and we have the resource place that is also in the initial marking. Then from this such a marking, we can find transition T1 with one of the variables, for example z, and we obtain x and y still remaining in idle, and z going to place waiting, and the resource res still there. So that gives this new marking. And you can see that whatever the value of x, y, and z, you can apply this thing. They're just different. So then we obtain the actual firings by testing all possible instantiations of the variables x, z, and y, x, y, and z. Yeah. Okay, so now let's consider permutations on bags. So we have a set A. We take a permutation on A, which we call S, and a bag small a of elements in A. So we can apply here the permutation to the bag SA, and this application of the permutation to the bag is the same as applying the permutation to the sum of elements in the bag, and it's the same as the sum of elements where the permutation, the sum of elements where the permutation is applied to the individual values. Right, which is what you have here. So the permutation, you can apply it to a bag, or you can apply it to the individual elements one by one, and that is exactly the same result. We have some properties. So in particular, if we apply twice the permutation, we obtain the initial element. So this is that part. And here we have an example. So let's take a bag C1 plus 2 C2 on the set C1, C2, C3. Let's take a permutation S such that C1 becomes C3, C2 becomes C1, and C3 becomes C2. If we apply this permutation to the bag A, we obtain S of C1 plus 2 C2. That is S of C1 plus 2 S of C2, because you can apply it to the individual elements. And that is C3 plus 2 C1. Right. So it's quite easy. Okay. So at this stage, you know about symmetric nets with their syntax and semantics. You have an intuitive idea about the notion of symmetries in symmetric net. And now we'll study formally these symmetries and how to use them for the construction of a reduced reachability graph, and we'll do that in the next sequence.